In this video, we present 𝒟-Attn, decomposed attention for large vision and language models, accepted by ICCV 2025. My name is Chia-Wen from ByteDance's Intelligent Creation team. You can find our GitHub code and archive paper following the QR code below. Current multimodal models treat and process visual and textual tokens in the same entangled way, making it difficult to analyze the interaction between visual and textual tokens within the LLM. Therefore, in this paper, we first propose a framework for analyzing the interaction between visual and textual tokens in the multimodal model. Built upon this framework, we identify several weaknesses in current multimodal models and propose fixes to enhance the model's multimodal capability. In the figure below, a vanilla self-attention model makes several mistakes in describing the diamond head photo, while our 𝒟-Attn model is able to describe the scene in a more comprehensive and precise way. To analyze the interaction between visual and textual tokens within a multimodal model, we decompose self-attention in an LLM into V2V self-attention, T2V cross-attention, and T2T self-attention. In this decomposition, V2V self-attention remains unchanged, while T2V cross-attention and T2T self-attention need to be merged with weights proportional to their log sum of exponentials. This is exactly where and how visual and textual tokens interact within the LLM. Please refer to our paper for detailed derivations. And with this decomposition, we now understand how visual and textual tokens interact within the LLM, allowing us to analyze and enhance each attention component separately and more easily. By analyzing the decomposed attention, we first observe that in V2V self-attention, the attention weights mainly concentrates on the diagonal, motivating us to diagonalize the V2V self-attention. And with this diagonalization, we reduce the computational complexity for the visual tokens from quadratic to linear, which effectively speeds up training by 5 times and increases the multimodal input length by 8 times. Furthermore, in our experiment, we observe minimal to no loss in multimodal performance with this diagonalization. We also observe that in T2V cross-attention, 1D positional encodings introduce a biased pattern in attention, where tokens closer in the input 1D sequence have higher attention values. For example, in the top left figure, a textual token at P7 has higher attention weight to the visual token at P6 than the visual token at P0, leading to a skewed and non-uniform attention pattern from each textual token to all visual tokens. To address this issue, we propose to set a uniform position ID to visual tokens as shown in the bottom left figure. This eliminates the positional bias and leads to a comprehensive understanding of visual contents, and thus stronger multimodal performance. With the proposed improvements, our 𝒟-Attn outperforms its self-attention counterpart consistently across 10 image benchmarks, with Mistral V0.3 as well as Llama2 LLM backbones. And in our ablations, the model with V2V diagonalization can train 5 times faster and take 8 times longer multimodal inputs while maintaining the multimodal performance. Also, by incorporating the biased positional encodings, our model achieves substantial performance improvement. On the image benchmarks shown in the tables below, our 𝒟-Attn excels particularly in tasks requiring spatial and relational reasoning, as well as OCR and document understanding. These results demonstrate the effectiveness of our proposed biased positional encoding. Thanks for listening. If you're interested in our work, feel free to stop by our poster presentation on Thursday morning. You can also find the GitHub code and archive paper from the QR code below.